Great. Lesson 5.2 is about exponential functions and graphs. It may seem unrelated to 5.1 where we talked about inverse functions because we're not doing really inverses today. But in 5.3, our next lesson, we will actually start looking at the inverses of these exponential functions. So it will become related. So first of all, an exponential function, what it is. This is the definition, but taking you through really what we're saying here. X, our variable, will be up in the exponent. And our base for the variable, because anything raised to a power is a base, our base will be the number. So you can see a couple of examples here like 2 to the x or 1/2 to the x. Now, we do have a couple of stipulations about what we're raising to the power, and one of them is that it's got to be positive. If it's not positive, then the graph would actually like jump back and forth, because just imagine if I had a -2 here, and I took -2 and raised it to the first, I would get a negative. But when I squared it, I would get a positive. When I cubed it, I would get a negative. And so the graph just kind of, it just kind of jumps back and forth. So if we keep it positive, then we'll constantly get the same sign. The other thing is that a cannot equal 1. That's because if this base were 1, then no matter what you raised it to, you would get 1, and the graph would just be a straight line. So when we look at, though, keeping it positive and not 1, then we get some very connected features. So we're going to really look at the commonalities here. Now, you and I both know I won't be able to graph really well on this online feature, but hopefully we'll get the idea of it, and then I'll bring up the calculator so you can see it really nicely. But if I were to just make a table of values, and the ones I like to plug in are -1, 0, and 1. We'll save this -1 for just a minute. Anything raised to the 0 power is equal to 1. Anything raised to the first power is equal to itself. So see, those points were very easy for me to do. Now, when you raise something to the -1, what you may not remember is a negative exponent is simply a notation to move it across the fraction bar. So the 2 that like was above the understood fraction bar has to move down, and so we get 1/2. So really raising something to the -1 just flips it over. If I have -1, 1/2, and you can see I've gotten a grid mark here that is really enlarged, so I can get this on here. 0, 1, and then 1, 2. Now these are not really lined up. It's going to be a curve. And if I can make it, we know it won't really be smooth when I do it, but that's what it would be, because actually if I plugged in a -2, then this would be 1/4. Okay, so it would be right here. So what happens is that if I could, we know that this should be a nice smooth curve, but there's the idea of it. Also, it levels off because this thing is never going to equal 0. A 2 raised to a positive number, or raised to even a negative number, because that's just going to make it a fraction. It's never going to equal 0. I'm always going to get a positive value. So actually, this is an asymptote. It's a horizontal asymptote here. Now, this one then is headed up. We call that growth. I hope that makes sense. But it's exponential growth then. And it's like the further you go on the x-axis, the faster you go up. On the other hand, this one, if I were to make a table of values, if I raise it to the 1, I get itself. Anything raised to the 0 is 1. And if I raise it to the -1, it actually just moves both of these numbers across the fraction bar, or in other words, flips it over. So that becomes 2. So at -1, we get 2. At 0, we have 1. And at 1, we have 1/2. So what you can see is actually this one is headed this other direction, and it really should have hit like right there. I just have trouble doing that online. And so again, that x-axis is going to be a horizontal asymptote. Now, what are the commonalities then? I kind of have them summarized on the next page, but you can see here that they're smooth. Well, I don't know that you can actually see that on my graph, but they don't jump around. There's no skipped spaces. They're continuous, and they're also one-to-one. So let's just look at it nicely here. So this is the conditions that we had to meet for an exponential function. Our base has to be positive and can equal 1. And then these are actually the commonalities. It's continuous. It's all connected. It's one-to-one. The reason that's important is because we learned in our last section in 5.1 that if a function is one-to-one, its inverse is also a function. So when we learn to take an inverse of these, it will also be a function. The domain of both of them went from negative infinity to infinity, and this is definitely a typo. The range on both of them started at 0 because they had that horizontal asymptote. So they went from 0 to infinity. Now, when a was a positive number greater than 1, that's where you saw it headed up on growth. And then when it was less than 1, we saw it decay. It's actually what that one's called. I didn't write that on there, but this one is growth and this one is decay, decreasing decay. They both had a horizontal asymptote at the x-axis, and they both had a y-intercept at 0, 1, because when we plug in a 0, we get 1. These are the 3 points that I use to graph all the time, and these are the key points that I can use when we have shifts also, because we're going to be doing that. So when you raise something to the -1, you just get the reciprocal. Anything raised to the 0 is 1, and anything raised to the 1 is itself. Okay, so those are our 3 key points to use. But we can take that same graph we've had before, and we can do all of our transformations with it. So let's kind of do 2 things here. I don't know, I'm not really going to graph them all, but numbers with the x are deceptive. Don't forget that we say insiders lie. So let's look at what these would be. This is grouped with the x, so it's definitely something horizontal. And it looks like a -2, which actually then is a shift of 2 to the right. This one is not grouped with the x. It's not part of the exponent. So this one is down 4 units because it's affecting the y values and it's not lying. Now, this one has 2 transformations happening. I would point out that this negative is not being raised to the power. So that base is still 2. It's just that we've got a negative multiplied to everything. If the negative were raised to the power, they would have to have parentheses around it. So we have 2 transformations we're looking at there. What the negative in front does, because that's a y thing, is it's a reflection. It's going to reflect it over the x-axis. Now the 3 is grouped with the x, and it's multiplied. Things that are multiplied are either a stretch or a compression. But the x one lies. This looks like it would get bigger, which actually means it's a horizontal compression of 1/3. Okay, so in other words, it would only take 1/3. Instead of saying, oh, I'm going to go over 1 and get a 1, you would just go over 1/3 and then you get a 1. Okay, but just remember that with the x, it's lying. Okay, now here I have a negative and it's in front of the x. So this is a reflection. It's just in front of it, but it's a reflection over the y-axis. I need to really bring your attention down here to this one. This negative x plus 4 and negative parentheses x minus 4. Those are the same thing. Because if I took this negative right here and I distributed it, negative times x is going to give me the negative x, and negative times negative 4 will give me the positive 4. The order of operations when you're dealing with them seems a little bit different. So let me just kind of write this out here bigger. If we did a to the negative x plus 4, this one would indicate that we needed to do a reflection over the y-axis and then shift 4 units to the left. If we write it like this, a to the negative x minus 4, this one is a shift, because I'm starting inside the parentheses, 4 to the right, and then a reflection. They end up at the same place. It's a little bit hard to imagine that, but if you take the point 1, 1, let's just take that point. If I reflect it, it ends up here. And then if I move it 4 to the left, 1, 2, 3, 4, it would end up right here. Okay? So I reflected it and then shifted it. On the other hand, if you take this point 1, 1 and you move it to the right 4 units and then reflect it, it ends up over there. So you can see the concept that they end up at the same place. So why am I spending so much time talking about this? Because unfortunately, on your homework, the computer doesn't seem to know that they're the same. I cannot remember for sure which one it wants. This is only going to happen though when you have both of those shifts, or both the reflection and the shift. It wasn't an issue up here when you only had, like here, I only had a shift with the x's. Here I only had the compression. Over here you only had the reflection. So those are never going to be a problem. But when you have both the shift and either a compression or stretch or reflection, if you have the shift and something else, your homework's going to be picky. So just be aware these two things will do the same thing. If you enter something and it marks it wrong, try it the other way, okay? And I wish I could take care of that for you, but you just have to be aware of that. Ladies and gentlemen, if you've not yet met E, I would like to introduce you to the number E. E is a number. You might say it is pi's cousin. They are both irrational numbers. You're used to dealing with pi because it's involved in all the geometry things that we deal with. You might not have met E before. E is also just about 3, but instead of being a little more than 3, it's a little less than 3. It's approximately 2.72. Now there is a key on your calculator, so let me just bring up the calculator for a minute. It is the second function. I want to get this big so that you can really see it here. Okay, so e to the x is right here in blue above your ln. You also have an e over here above in blue above your divide. This one is the one we will use most often because generally when you are dealing with things with e, you need to raise them to a power. So when you choose second ln, it is going to give you an e and be ready to enter the power immediately. Okay, so let me just put that. On the other hand, if you use second divide, it enters the e and it doesn't have a power mark there. So they both work, it's just whichever one you need. So E is approximately 2.72. Now, this is the exponential growth graph of e to the x then. We still get 1 right here because anything raised to the 0 is 1. Now this value is 1, 2.718. That's because that's e. It's not really, that's rounded, it's just rounded a bit further out. But this one is growth, so it also has transformations, just like we were just looking at. So let's look at these, and when you are doing homework, if you have multiple choice, I'm going to tell you there are a lot of things you could do, but generally speaking, what you want to do is look at the equation long enough that you figure out where the asymptote is. An asymptote is generally at the x-axis unless it has a vertical shift. So you're going to look at where that asymptote is, and then generally which shape should you be looking at. And most of them you can figure out that way. When I look at this number at the end, this is really telling me where that asymptote has been shifted. So instead of being at 0, those are the values it would be at. Now this one seems to be written a little bit different, but this is where the asymptote is because I could rewrite that one as negative e to the x plus 1. All right, so that's asymptotes. Now, what I can see here is that if it's 2 to the x, I know it would have been growth. But this reflected it, and it takes those positive values and makes them negative. So instead of going up, it actually is going to go down. So I'm looking for something like this shape that has an asymptote at -1. Now, one of the things you can visually kind of do on your, I probably just need to make that smaller there. One of the things you can do over here is kind of look at where you see a graph level off, because our lines, it's not really supposed to ever get exactly level, but it's going to look like it. And you just kind of visually kind of draw that out. And that's where your asymptote is showing up. So see this one here, it's going to be at 1. This one's at 3. And this one's at -1. So you can visualize where those asymptotes are. So now if you look at this, I said it's got an arc down, and it's going to have an asymptote at -1. This is the only one we had even with an asymptote at -1. So F has to go with number 1. Now this one has to have an asymptote at 3, but e to the x curves up. See, there's my asymptote at 3, and it is curving up. So that's E. So these are kind of the key features you're going to look for, and the ones that are more difficult are the ones with shifts. So that's going to be this one. But this one, I know my asymptote is at -2, and if you look at my options, I already know it's got to be A. But let's talk about this. This 3, it would have headed up. The negative in front of the x made it reflect over like that. So it had that shape, and then -2. And of course, you could punch these into your graphing calculator and look at it, but even that might not be necessary. 1/2 to the x would typically go down, but a negative in front has flipped it all over the x-axis, so it should be looking like that. And the horizontal asymptote didn't move. This one, well, let me do number 6 next, because actually this one is the hardest one to see, although we'll point it out to you. This one, I know it's got that asymptote at 1. So out of what's left, it's got to be D. And yet, the reason it's headed down is because this in the front took what was headed up and it flipped it over. Okay? So that one's D. And once we have that figured out, I bet this other one is B. But when you look at this one, it's a little bit harder to say. I know it's shaped like that and my asymptote didn't move. But it does have this horizontal shift that moved it to the left 1 unit. That's where if you have to look at something closely, you want to look at points. Normally, these things cross right here at 1, but you can see that that has been shifted to the left 1 unit. Okay? So you can see that shift, but a horizontal shift looks a lot like a vertical one because that one could have gone up. So you gotta just have to narrow it down. There won't be tons of those. Usually, though, it's not too bad to match the correct graph. All right, so I said that this lesson was about exponential functions and compound interest. We have 1 slide left, so this is our compound interest. There's a lot more on this slide than it looks like. We have 2 formulas for compound interest. Compounded a certain number of times each year, and then compounded continuously. And here we can see our new friend E. Now, in case you're not familiar with what the letters mean, P is your starting amount. It stands for principal. That could be money that you start off taking out in a loan or that you start off depositing in an investment or something, okay? R is your rate as a decimal. Now, a note about that. When I say as a decimal, I mean not as a percentage. So here I do see an R, but notice it's got this percent. In order for you to get it as a decimal, despite the fact that it has this decimal in it, what we're really saying is move that decimal 2 places to the left and then don't use a percentage sign, okay? So that is the rate here is going to be 0.045. Now T is time in years. It is important you note that. You might not need it, but if they told you that they were investing something for 6 months, then T would be half a year, 1/2. If they said they were investing it for 5 months, you would have to use 5 over 12, you know, as a fraction of a year. T needs to be in years. Now, E is not something that's going to represent anything because that is actually a number. It just doesn't look like it. It's the number in disguise. And N, I didn't write down because they've already told us over here it's compounded N times each year. So then the only thing we haven't identified in A, and A is the amount, it's really called the future value. It's the amount in the account later, okay? It's the final amount. So I'm just going to write that over here. I kind of ran out of room over there. So that it's the amount at the end of this period of time. Okay, so suppose $100,000 is invested. Well, $100,000 then is P. It's in an account that pays 4.5% interest, so I've got my R up here as 0.045. It's left for 5 years, so that is T. How much money will be in the account after the interest is compounded? That means I am solving this stuff for A. Now, what is N then? How often are they compounded? That actually is parts A, B, C, D, E, and F. N is changing in all of these. If you compound something annually, N is just 1. It just means 1 time a year. Semi-annually is twice a year. Quarterly then refers to 4 times a year. Monthly is 12 times a year. And daily, well, we didn't want you to think it was leap year. We have 365 days in our regular years. Continuously is the other formula. So we're going to use this formula for parts A through E, and then this one will be for part F. Now, I've got a thing here. This is an excellent use of that copy and paste feature in the calculator. I'm going to type all this in for the first one, and then I'll just be editing it for the others. So we'll bring up the calculator. I'm going to kind of move it over and kind of resize so that you can actually see the display screen bigger. That's the more important one for us. And I'm going to enter this with our information. So P was 100,000. That's 5 zeros. And then I've got parentheses, 1 plus. By the way, putting that 1 in there is what adds in your first 100,000. And then the other part is going to calculate the interest. Alpha y equals, enter. The numerator is R, so that was 0.045. N, now I know putting it over 1 seems kind of useless right now, but because I don't want to retype this entire equation, I just want to edit it. I'm kind of putting that 1 there as a placeholder for my number. And then I have n times t, so that's going to be 1 times 5. Now, in the future, for my next couple of problems, I'll just have to edit this 1 because everything else is going to stay the same. So 1 time a year, man, 5 years later, I've gained almost $25,000. Okay? I'm going to go up and then hit enter. Then I can just go backwards and change my 1 to a 2. But don't forget to change it both places. And now this is going to be for twice a year or semi-annually. Oh, doing it semi-annually, I got about another $300. Maybe not as big of a jump as you would think since they compounded it twice as often. I mean, you got 24,600 doing it once a year. We only get 24,900 doing it twice a year. I can also hit second enter, and it will copy it from what I did last time, so that's another way that you can redo it. But now if I'm going to do it quarterly, I need to change the 2 to a 4. Okay, now I'm going to take a moment and write some of these down because when I do my next one, this one's going to probably roll off the screen. So you can see these values, though. When I did it 4 times a year, it still went up, but notice it didn't even go up as much. When I doubled the number of times it was compounded here, I got an extra 300. When I doubled it again, I just got a 100 roughly, okay, 150. So it's not so much as you would think. So let me move this so that I can see it on another screen while I copy it down, and then we'll bring it back. Okay, now I need to do monthly and daily with this same formula. So if I do it monthly, again, you can just click up a couple times or you can hit second enter. Monthly, I need to change my 4s to a 12. Now in the denominator, it'll just let me type both of them. But right here, since I need to get a 12 there, I'm either going to have to retype that, or if I want to move that times thing over, I can hit second delete, which is actually my insert feature. So now it's moved it over. So there's 12 times a year, so that's monthly. Okay, so look at monthly. I got an extra $104 instead of $150, even though I did it 3 times more often than the other one. It's always going up, but it's not going up by as much. What that really indicates is kind of a calculus notion that it's approaching a limit. There's a level where it's going to stop. Okay, so now instead of monthly, I need to do it daily. I've got to change that 12 out to a 365. Typed over that one. Here I'm going to type over the first 2 digits and then insert my 5. Okay, so look, now I've only gained $50, even though I'm doing it every single day. All right, let me bring this over and I'm going to write down those answers. Now, I know it didn't ask us this, but what I'm going to do is let's increase this by a lot. What if we did it 10 times a day? If we did it 10 times a day, that would be 3,650 times a year. So I'm going to do one more of these. Okay, if we did this 10 times a day, look now, I've only gained an extra $2. So you can see it's going up, but it's going up less and less and less. Well, eventually, then no matter how often they do it, it's going to round to the same amount. And that's what this formula is about. This formula is so much easier to deal with, and yet the difference between this formula and using the more specific one is so small, it becomes negligible over time. So if this one is the one that they say is continuously, because it's 10 times a day, I could have made this 100 times a day, and it would be almost no difference. I know I said I was only going to do one more, but I'm going to add another 0 just so you can see that, and then we'll do the continuous one. So putting an extra 0 on here would be like they were compounding my interest 100 times a day. Look, that only changed it 16 cents. 15 cents really, because that one rounded to a dime. That's just a change of 15 cents. So you can see if they do it 100 times a day as opposed to 10, I only got an extra 15 cents. Then if they did it continuously, it's not going to make much difference. But we do have a much easier formula for it. So now using the easier formula, I take my 100,000 times E. That's where I hit second ln, e to the RT, so I do have my R times T. So this is the formula, which I often refer to that. You can, if you look at the formula, you know why. It's the PERT formula. PERT is continuous. And notice the difference between continuous and 100 times a day was just 2 cents. And that formula was probably worth 2 cents because it's so much better. 125, 232, 27. And part F then came from this formula. All right, that finishes up this lesson. I'll be looking for your emails. If you get stuck, ask the instructor.